Right.
Perfect.
That's it. Hard work. It's hard work keeping quiet, isn't it? Anyway,
Yeah. I was okay.
hi
Yeah,
Matthew. Welcome. Welcome, sir. How are you today?
I'm doing well. I worked really hard on getting my office background. And for
Yeah.
those, I'm actually in the Oracle's Broomfield office, formerly the Sun campus, for those who go that far back.
Oh, nice.
That would be the Flatirons outside of
Oh,
Boulder. You guys come to visit on the top of
that's really good.
actually in-person events and being around people. We've since early April, we've been coming into the office has been open and groups are
That's really good. Huh? Coming back to socialize a little bit. Not just work,
Yeah.
from home.
Well, and I know it's probably not important to skinny people like you, but I put my suit on for the first time in ages to go onto a customer site last week and discovered it was too big for me. So I was a very happy boy. But anyway, um, so maybe without further ado, let's introduce Matthew.
Yeah.
Obviously, I've got some fun facts, but
Wow. So
uh,
I will do
the
the
normal,
the
yeah,
classic, the normal part, and you will say something
yeah.
that we don't know about Matt. Okay, so thank you so much, Matt, for being here. Matt is a principal data scientist working in Oracle advertising. And the focus of his work is researching to integrate new data sources while reducing bias and improving factor up. Matt is also, this is very important, Matt is also a co-founder of the Denver R user group that they regularly they meet together and discuss all things about R, obviously, and have a few drinks. Awesome.
Very good. So yeah, some of the fun facts. I've been probing everybody to get something interesting that they've done, and so Matthew used to work for 8 years at the National Center for Atmospheric Research in forecast verification. So basically, he was telling them just how wrong they were, and he would he basically give them new metrics to show how poor they were at actually forecasting. He's an avid bike ride. By the way, I did assume this was a bicycle and not a motorcycle.
Mhm.
Either would be a good journey, but Matthew's ridden across the US twice. He's done Oregon to Maine and California to Georgia. So yeah,
Wow.
so I'm in awe of that. I'm a motorcyclist myself, and I would do the journey on my bike, but not on a bicycle. Thank you very much.
Our
So
colleagues from here head up to Sturgis.
yeah, good.
Well,
So without further
yeah.
ado, I will pass it to you.
All right.
Well, it's yeah. So just one small thing to our attendees. Please submit your questions in the Q&A box instead of the chat box, and that's it. Just that. The audience is yours, Matt.
Yeah, thank you, sir.
All right. I'd like to thank everyone for the opportunity to speak to this group. And yeah, my name is Matt Pocernich. I work in Oracle advertising, and I am a data scientist slash statistician in support of the Moat Reach project. And I'll have a slide about what that is to give context. And I'll be talking about how we make better use of all the different types of imperfect data we have available. And so, very brief outline, I'll provide some context into the problems we work on, the data, a couple minutes on statistics, the methods we use for weighting, jump into a demo, and then a few words about results and workflow. So, context. So, to jump to the chase, this is what our group sells. This is Moat Reach, and it helps advertisers identify across a lot of different platforms who they're reaching, both on the individual level and the household level, and what audiences they're reaching, and they can break it down by campaign. And pertinent to the example and the problems I'll be addressing in the next few minutes is, so the clients see this, we could see that here they have reached 105 million households, each 80 times. And the Venn diagram down at the bottom says you've reached this proportion with TV, digital, or connected TV. And obviously this appears seamless. This appears like we have magical source of data that lets us either see all households. Obviously, no one really believes that. And unfortunately, we don't even have a random sample of households or individuals, and we don't have complete insight on households or individuals. So my group's job is to take disparate sources of information, bring them together in a responsible way, and get the best information we can out to our clients. And I'm gonna focus on TV. And so drilling down a little bit deeper, we provide information that would say for given sets of parameters, you've reached at the individual level. The main demographic breakdown we would give would be age and gender, but like this candy company would have reached, you know, more people on digital in the younger ages, more people in TV on the older ages. But in order to do this, we need, again, to take advantage of a bunch of different sources of data. And again, the data we have available is not random. So hence we're going to be talking about weighting. All right, the data. This is a high level view of our data flow. To power that dashboard, we have our impressions collected from a variety of sources. The two I'll be talking about is, so we have a large scale TV source, and this would be data that's collected from a smart TV, such as Vizio TVs. If you have a smart TV and you've set it up, connected it to your internet and just hit okay on the up front boxes, at some point you've agreed to have your content monitored, and it's collected and used by advertisers and people like us. It's it's IDs are hashed and all, and privacy is protected. I'll just leave it at that. We have a smaller panel, and this is what I'll be using for an example. And these is 5,000 households. So for scale, large would be 16 million TVs we could get data from on any given day. Panel household is 5,000. And we also bring in connected TV, digital, glue it all together with a ID graph and do some statistics. This is how we represent statistics. And what we'll be talking about is, you know, we do a number of things in the methodology, but one of the things we do is correct for bias. And that's what I'd like to, that's the topic I will be talking about in terms of this example. And our big goal is we get television data, either our small TV data or our big TV data, and want it. It's not explicitly stated on the dashboard, but it's understood that, you know, without any other caveats, this is out of the US population. So out of the 128 million households in the US, this is household representatives. Out of the 270 million adults, and all the data we process is for people 18 and older. We want to scale to that number. So we need to make adjustments from both our panel and our large scale to reflect census values. Okay. All right. A little bit about the method I'll be illustrating. It's called raking. It has a number of different other different names, iterative, proportional, fitting, and rim weighting, but I like the name raking because it does kind of explain what is being done. It is a way to basically weight our records based on a number of different attributes. And the chief reason we, and many people in survey statistics, use this information is when you don't have information on joint distributions. And to illustrate this point, you know, from the census, you can get breakdown on household size, number of households with 1 or 2 adults, 3 or 4, 5 or more. You can get breakdowns by income, but the census doesn't report on the joint distributions for household and income together. And so we can't directly weight to that. So we have marginal information for our target populations. And more granular information for our sample data. And a quick word on naming convention. So sample is, I'll use sample in my code and stuff, and that is representing the data that we collect, and target is the global population which we would like to reflect. So in this example, we actually have values for number of our records that are in a given size and income. And what ranking does is kind of iteratively going, again, why the name is good, across one dimension to the next dimension. But first, let's say by household income, it is going to adjust the household income counts so that it reflects our target population proportions. And in doing so, it's going to mess up the household size population. So we're going to, then you would make an adjustment in the next dimension, in this case, household size. And you basically iteratively, and that's why it's in the other name, you're going to iteratively move back and forth until the weights allow you to get proportions that are not changing drastically, or essentially things converge. And this is 2 dimensions, but this works in many more, multiple dimensions. There are costs, and we'll talk a little bit about that as well. Speaking of cost, yes, there's no such thing as a free lunch. We can't put in as many attributes as we would like, as you could think of. There's costs associated with the number, how you break up your data, and that gets into more data exploration and well, there's no free lunch is a good way to just summarize it. And there's measures to see how much you've tortured your data to kind of get it to represent what you want it to, and less torture or less ways of like kind of heavily weighting the data would be viewed to be better. We have a couple levers to pull and guidelines to follow. At a very high level, we want to choose, and you would choose attributes that are relevant to the outcome you're trying to measure. So we're interested in TV viewing, and so we use what's available, but also what's relevant. Income, education level speaks to how much TV people might watch. Age, certainly older people watch more than younger people, particularly linearly streamed TV. Area around the country gets used, but not so much. In this example, we'd like to have that just to make sure we have national representation. We get to adjust and define the bucket sizes. We'd like them to be defined in a way that they are not, they're plausibly and relatively homogeneous between our target and our sample data. There's some opportunities to collapsing marginal information where like age and gender, you could actually get joint distributions. You couldn't do it with like income and it's not always possible. And we also would limit the maximum weight assigned to a given individual. And this kind of will bring you into a bias variance trade-off. Okay, demo, and now I'm going to switch gears here for a moment. 2 slides before I switch gears. So my background's in statistics, so I've kind of moved along the path of I'm a kind of a passionate R user. When RStudio came along in 2010-11, I began using that, pointing it to different backends, and I'll comment to this a little bit at the end as well. And now here at Oracle, with our data having been moved largely to Exadatas, we're moving to OML for R. The package I will be demonstrating is called Iterate, and basically the steps we're going to be following is we need to define our target by choosing the attributes we're going to weight on, define the bins, and then check our sample data to make sure that the bins and labels are consistent essentially. And then the iterate function, and this is something that is available publicly in R, you basically create an input list, compute, evaluate, and compare. So let me switch over to, okay, this is, how was I talking about my other workspace. So, don't know the familiarity. Mark mentioned that everyone here doesn't use R, which is a choice. So what I'm going to be doing and looking at is basically, this is our studio IDE. This is where I spend most of my days. And for those those unfamiliar, this would be the code, the console, objects in my environment, and then the lower right-hand corner would give me other information like files and panes. And what I'll be looking through here is examples of code. And this is in a markdown type document, which if I compile it, or when I run the whole thing, it'll give me a number of outputs, including an HTML document. And so, excuse me, of course. So anyway, back to my workspace. What I need to do first is define, I'm reading data from a database. And so this is just a template I use on top of all my code. So these are packages I use, most notably to read the data, get data. The Exadata would be OR for dplyr and OR the library. I make a connection, and I would have data frames located, or data tables accessible here. The first step I would like to do is define a couple target objects. And here, make that a little bigger. Here, basically, I am taking a table and then using the R package called dplyr, and this just allows me to, if you've not seen this before, it's a wrapper that kind of allows me to filter and operate and split and aggregate tables in a very, I think, elegant way. And so I'm taking this table, I'm doing some filtering, I'm adding some columns, doing some relabeling, doing some grouping, doing some recalculation, and some doing some calculation, ungrouping, so then I could do another calculation at another group by level. The arrows within the parentheses is just essentially piping, and what this is doing is giving me an object that has, this is a small table that, let's create, gives me my age bins and properties, proportions. So this is just looking at age alone. This is based on a table, target pops is a table we've created that has our census values for household income, rural, well, that's where we put all our target data. We'll do something similar for, if I want to bring age and gender together, again, here, I'll talk about this a little bit on the end. In my environment, I have some objects that are existing on the Exadata and some things that I'm pulling in locally. This is an example where I'm pulling in a table to work on it locally on the R machine. Otherwise, it's doing operations on the Exadata and it's not here. And I'm basically redefining relabeling some names and producing another target table. Income. And I'm trying to keep track of time to keep myself in line. Household size. My sample table, and this sample data has been randomized and is a subset of our full table, but basically I have households and individuals and all the fields that I've defined before, as well as bins that I've created. So using the same steps, I just need to make sure that both my sample data frames and my target data frames are consistent. Define household sizes from the table. A slight brute force modification in that the census only goes to households 7 and bigger, and in our panel data we have a couple households with more than 7 adults. And finally, the steps, and I'm going to do a little movement here. The steps needed to run the iterate function. The input is essentially a list, and here we're just basically gluing our sample data and our targets together into a list using the universe function. That gives me a list of, so here I'm taking my sample data, I'm saying I want to use the following attributes: household size, gender, and age, and give me weights for each individual in my sample data record so that my marginals match. And this is small data. This is 10,000 rows. These are individuals and 5,000 households that have volunteered to have their TV watching very closely viewed. But the function kind of comes through and says, okay, you started with 8,700 records, and the effective sample size, and this is one of the quality metrics, says you basically have information from equivalent to the 6,700 members. And so we can calculate an efficiency number. And for comparing between different types of selections of attributes, higher efficiencies, better. The function also takes into account ordering of the individuals, because which dimension you rake first can impact, although not always, your results. And then to compare our results, there's a compare function. And again, this is randomized data, so this isn't, don't draw conclusions about TV viewing here, but we could see the red dots represent our unweighted population. The black line represents our target, and the blue dot represents the weighted proportion for each bin. So with this number of dimensions, we can see that we have, successfully weighted at a reasonable level of efficiency across these dimensions. And I'm going to take a peek at my markdown for the, so I don't run out of time. But basically, in the markdown document from the same code, this would show the list we've created. This is the output. And this would show the relative, the weight that gets assigned to each individual based on their what kind of type of household. The graphs which we just saw, this is a table summary of the graph. I was curious, so for age and gender, I mentioned for that, those two variables, we can fold them into one another. So we could make another list, do a comparison. And essentially these aren't, the results aren't the same, but there was little to be gained by bringing them together, the same level of efficiency. And age level, age, gender, household size, income. Here, we take a hit on efficiency by including them all. Again, basically in our sample data, we tend to have too many people living, too many households with one person in them. So this requires more weighting. And again, there's no free lunch. And I could bring this together to compare a number of iterations quickly and painlessly. All right. I'm gonna go back to my deck here. So as I mentioned, yeah, my work world, oh wait, back. This is more real data. Our target population here, we're basically underrepresented in people over the age of 65. Something that we grapple with is people, there is by age definitely a loss of people with access to internet as in the older age demographics. But we have too few people living alone, too many people living together. So the household fitting for the household size comes at a cost. We use the same method, and we've developed the same method using our large scale data. We have a few more attributes we included with that. Age, presence of children, urban, rural, and geography. And this would be a similar example with our big data. And we do this nightly because the number of TVs in our population changes slightly day to day. And so this all gets done every night. We get new weights every night. For our Vizio TVs that are distributed geographically, we don't often get things randomly distributed, but the TVs are Vizio TVs, and we've also looked at other brand names that similar information, with one or two exceptions, are spread nicely across the country. A word about workflow and the technology I use before I run out of time. As I've mentioned, I've been using RStudio forever, or R forever, RStudio since it was born. Pointing the back end to a number of different platforms. I've certainly used it on a desktop. I've used it pointing to servers where I've used R and batch to kind of gather data, like at NCAR to run overnight and get the data I wanted. We have been using them on our AWS clouds, but as our group has moved all our data down to Exadata, this has brought me into using OML for R, which Mark could certainly speak more to the efficiency, but I would like to speak at least to the similarity in that from a data scientist, this is all very comforting in that on the front end and the code and my environment, much has remained consistent. The back end has gone from being a desktop to being an Exadata. There's certainly, I'm not using 10,000 rows. I could be using 20 million, 50 million, 100 million rows on the back end. The dplyr is a tool I use a lot. The heavy lifting of that within OML for R is done on the Exadatas with R on the Exadatas. But as a user, it is very nice in that things have not changed. So the takeaways. Using the iterate package from R, we were able to quickly evaluate a number of different weighting algorithms and found them to work well for our needs. We were able to leverage an existing package, wrangle different sources of data populations and playing with that, so that makes things move quickly. evaluate new weights, bringing in R studio and OML for R. Again, there's gains to be made certainly in efficiencies and by bringing R closer to the data that we're using. We're not moving the data, we're moving R. But from, again, a user with a statistical background, the fact that it just extends usage of, for example, dplyr, with all the heavy lifting being done on the Exadata, is not me bringing all the data into a data frame and manipulating. That has been very nice. And I believe I am right at time.
Yeah, perfect, Matthew. You know, I used to hate statistics when I was finishing it off at school. Only when I started to use it in real life for practical purpose did it really come alive for me. So thank you very much for that presentation. Very good. I think your passion for statistics definitely shines through. So I don't see any questions. Anyone else? I see Mark is about ready to go, and in fact, we're actually a minute into his time. So
I apologize, Mark.
there's a question. Anonymous attendee: is OML for R suited to automate these types of manipulations and integrations results in a dashboard for business end users? I
would defer the fully correct answer to that to our next speaker, Mark. I would say yes, but I use it from a researcher's role, so I'll let Mark say yes.
Hey, hi Matt. Hi Roger.
Hi Mark. There he is.
So I thought I'd just jump in to help with that. I think that the idea there is with embedded execution is something that can be used to leverage these third-party packages and then have the database spawn R engines to do those types of computations. And to avoid pulling the data out, you can just keep it in the database using the transparency layer. I came in a bit late because I had another presentation to give, but I believe Matthew probably already commented on that. And what I'll be talking about next is the OML for Pi SQL interface for embedded execution. So that will give you an idea of what we already have available for R on premises, and that will be adding to that for OML for R on autonomous database later this year. But that's really, I think, a nice way to tie what Matt's doing in with the OML for R in the database.
Brilliant. Well, thank you so much for your presentation, Matthew. And I even learned how to say your name, Pocernich, so I'll get you right next time. With that, thank you. I don't see any more questions. I'm going to intro Mark, and we'll just